This lesson's about the internal resistance of a cell, and here are your objectives. First, let's look at a simulation to get a sense of what we're talking about. This is a simulation from PhET. We've got a cell here connected in series with an ammeter. We have a resistor and a switch and a voltmeter connected across the terminals of the cell. Notice that the voltmeter reads 9 volts and there's no current flowing because the switch is open. Now watch what happens to the reading on the voltmeter as I close the switch and the current starts to flow. Notice that now the voltage is only 7.5 volts. When I open it back up, it's 9 volts. So something's happening as I complete the circuit and current flows that's changing the terminal potential difference, that's what I'm measuring here, across the cell. That's what we're going to try and understand. So to understand what's going on there, we need to recognize that a cell itself has some internal resistance to the flow of charges within it. And so we can think of a real cell as being an ideal cell with EMF epsilon in series with a resistor that has resistance R. So let me elaborate on that a little bit. The boundaries of the real physical cell are here, where I'm outlining in blue. And because this is the positive terminal, if you want to think about it looking like a cell that you're used to using, like a AA, then it might look like that. We can only actually connect the voltmeter to the terminals which are outside of where I've drawn the blue. So to measure the terminal potential difference, I'm measuring from here to here. Inside the cell, we can think of it as if there were a perfect cell, which of course doesn't exist, it's an abstraction, in series with a little resistor. And remember, EMF is the potential difference supplied by a power source. So this is EMF epsilon, and we have a little resistor which we're going to give the symbol lowercase r to. Now, of course, there's no real resistor in there. This is just our way of thinking about the resistance of the cell itself. And that's not there on purpose, it's just a function of the materials that the cell is built with. Now, of course, when we connect this into a circuit with a resistor, we have another external resistance, and we're going to give that the symbol capital R. So we know by the loop rule, therefore, that the total sum of the potential gains and drops around this series circuit must sum to 0. In other words, the EMF of the ideal cell minus the potential drop at the internal resistor, which is I times lowercase r. Remember that potential drop is equal to the current through a resistor times the resistance of that resistor. Here that's lowercase r. So the potential gain here, which is epsilon, minus the potential drop here, which is the current through that imaginary resistor times its resistance, minus that same current, because it's a series circuit, the current remains the same, times the resistance of the external resistor. So this is the voltage drop, the potential drop at the external resistor. And by the loop rule, that has to be equal to 0. In other words, rearranging, we get the EMF minus the potential drop at the internal resistance is equal to the potential drop at the external resistance. Now, the potential drop at the external resistance, if we were to measure it here, has to be the same as the reading on the voltmeter up here, because these are just connected to the same spot if we imagine that the wires have 0 resistance. So this here is our terminal potential difference. It's the reading that we would get if we connected the voltmeter to the outside of the physical cell. We would get the same reading down here as we would up here. And we're going to give the symbol for terminal potential difference as V. So just restating that, we have that the potential difference measured from one terminal of the whole cell to the other, which is again called the terminal potential difference, and we gave the symbol V2, is equal to the potential drop across the outside resistor, and this is I times capital R. We're just saying that V is equal to IR, in other words here. So now replacing this with V, we get this form of the equation. Our terminal potential difference is equal to the EMF minus the current times the internal resistance. And we can also restate that in a couple of other ways, which can be useful depending on what you're given, like this. Or moving everything to one side, you can get that the EMF is equal to the current times the sum of the two resistances that are in series, the external resistor and the internal resistance of the cell itself. So these are just different ways of saying the same thing. Let's think a little bit further now about the implications of this equation. So when no current is flowing, in other words, when I is equal to 0, this term cancels, and so the terminal potential difference, remember this is the terminal potential difference, equals the EMF of the ideal cell. And we give that the symbol epsilon. Remember that the EMF is just the potential difference that's being supplied by the power source. So it's in volts as well. So you've got the same units on either side. So when no current is flowing, the terminal potential difference equals the EMF of the ideal cell. And that's because no potential is being dropped at the internal resistance. This term has become 0. However, when current flows, the terminal potential difference is always less than the EMF by the amount I times little r. That's what this is showing. So back in the simulation here we see that the voltmeter is reading 9 volts when we have an open circuit. So this must be our EMF. No current is flowing, and so the terminal potential difference is equal to the EMF of the cell. When I close the circuit, now we see that it's dropped by 1.5 volts to 7.5 volts. So that means that I times lowercase r, the current multiplied by the internal resistance of the cell, is equal to 1.5 volts, because those are our lost volts when I close the circuit. And we could use that and our current to work out what the internal resistance of the cell is. It's also interesting to ask ourselves, what's the theoretical maximum current that a cell can provide? So if we start from this relationship, and we remember that this is our terminal potential difference, which is also equal to the current multiplied by the external resistance, then the maximum current that a cell can provide is in the case where it is short-circuited. So we take our cell, it's got an internal resistance like this, and we just connect the two terminals by a wire. In this case, the external resistance is equal to 0, and so this becomes 0, and we have 0 is equal to the EMF of the cell minus the current times the internal resistance. We're trying to solve for the current, so if we rearrange here, we get that the maximum current, I'll write that as I sub max, is equal to the EMF of the cell divided by its internal resistance. And this is why car batteries, which are only 12 volts, are able to provide such an enormous current, because they have a very small internal resistance. A small internal resistance is going to increase the current that they can provide. And this is part of why car batteries are so dangerous. If you accidentally short circuit them, you'll get an enormous current and start a fire or cause the car battery to explode. Let's finish up by talking about how you would actually experimentally determine the internal resistance of a given cell. So you'd use a setup like this. Here's the physical cell, inside of which we have the ideal EMF as well as the internal resistance, and then you've got a voltmeter connected across it. The voltmeter is going to measure the terminal potential difference, V, and we've got an ammeter to measure the current, and we have a variable resistor that we can change the resistance of. Now, using this equation, notice that this is in the form y is equal to mx plus b, our equation for a straight line, where y is equal to v, our terminal potential difference, b is equal to our EMF, this is b over here, x is our current, and our slope, therefore, is negative r. What that means is, if you change the current, and you measure the potential difference, you can generate a series of points that will lie along a straight line and give you the EMF as well as the value of the internal resistance. So if this is the terminal potential difference here that we're graphing on the y-axis, and if this is the current over here, then when we change the external resistance and measure both the current and the terminal potential difference, we'll get a straight line. So we'll see something that looks like this. And this value here is our EMF, and the slope of this line is negative the internal resistance. So once again, we're using this setup. We're measuring the terminal potential difference and the current as we change the external resistance, graphing that as a straight line, and then our y-intercept is the EMF of the cell, and the slope gives us negative of the internal resistance of the cell. So that's an introduction to the internal resistance of a cell and how you'd find it experimentally.